Hey, this is Leach with Simpson Math, and today we are going to be looking at rational functions, taking a much deeper dive into them, and looking at specifically the asymptotes and wholes. So the asymptotes and wholes. So just first, what is a rational function? So this is an example of 1 over x. We've graphed this previously, we've moved it around, we've stretched it, we've flipped it, we've shifted it. This is 1 over x. You should be quite familiar with this function, but what if instead of it being just 1 over x, what if it was 1 over x squared? So notice, again, we have asymptotes. We still have the same horizontal and vertical asymptote, but the relationship of the function is a little bit different. So we're going to be talking about a little bit more detail in next lecture about how to know where the dots are, but we're focusing on asymptotes and wholes today. So take a look at this one. This one we actually have 2 different vertical asymptotes and a horizontal asymptote of y equals 0. And then also, if I show you, here we go. I can move around and look at a few dots, and I want you to see what happens when I get directly on top of -2. We literally get what I call a hole. What we collectively in math community call a hole. It's just an empty spot in the function. So we're talking about what happens when that occurs. All right, so we can have asymptotes. So we have vertical asymptotes, 2 of them in this one, and a horizontal asymptote. All right, we have this one. We again have 2 vertical asymptotes, but then we have a horizontal asymptote that is not at y equals 0, but now at y equals 2. So it doesn't just have to be y equals 0, just like how we were able to shift things around. And then even we're going to be talking about something called a slant asymptote. So here we have a vertical asymptote at x equals 1, but then we have a slant asymptote that is going through we basically just have this diagonal line that the function is warping around instead of a horizontal line. So we'll be talking about a little bit more detail about what that is, but in our coming lectures, later lecture, we'll talk about how to find them, but we'll just be introducing the idea. So let's dive into the notes. All right, so let's talk about asymptotes and wholes. That's the title of this lecture. Here's just a little bit. It says, rational functions are functions in which are ratios of polynomials. We have a polynomial on top, polynomial on bottom. So let p of x and q of x be polynomials. Then f of x is a rational function where we have p of x over q of x. Before we dive too far into this, because we're going to be dealing with fractions, let's talk about this, what I call this killing kittens review. There's a meme out there. I might pop it up on the screen right here, where you're reducing or canceling incorrectly. So let's make sure we're clear about these next little 4 things. So if I see x plus 2 over x minus 2, nothing reduces. Students are tempted sometimes to try to reduce these x's and reduce these 2's and end up with like a -1 or something. That is a big, big, big no-no. You can only reduce when everything is being multiplied, when everything is factored, and then you can reduce common things on top and bottom because they're basically reducing to 1. It's like like 7 over 7 reduces to 1. It has to be that same thing in all multiplication. All right, what about the second one? Well, nothing reduces here. Students might be tempted to just cross through these x squareds, but again, that is not a good idea. Then what about, it doesn't work because we don't have, it's not all multiplication. But notice if I just simply, I know this is not common, but what if me, the teacher, were to write a new question where it's not adding and subtracting on bottom, but it's all multiplication? Well, then in this case, yes, you could reduce those x squareds, and then we are left with 1 over -8x. And then what about this last one? Yep, it does reduce. What I like to do when I do this reduction, I like to cross through that 2 and then cross through that x. If I have an exponent, that I can also just write that it's a 1. So like cross through, say that's a 1, and then cross through with that x. So reduce an x from the top and the bottom, and be left with just x halves. A general tip is if you think you're allowed to reduce it, plug in some numbers. Plug in some numbers and simplify, and then plug in numbers, reduce what you think reduces, and then see if you end up with the same answer. If you end up with a different answer, then that reduction was not legal. All right, so let's go back to the problem. Okay, let's take a look at this introductory example. So this lecture is about us getting our feet wet with understanding what an asymptote is. We have vertical and horizontal asymptotes, how to find them algebraically by just looking at the function, the equation of the function, and then also what are holes and how can we find their quadrants. Their not their quadrants, their coordinates. So let's take a look at this first one. This is a rational function. I have a polynomial over another polynomial. Um, just like when we talked about polynomials in the last several lectures, we have degrees of polynomials. Well, since I have a polynomial in the numerator and one in the denominator, I'm going to have what I refer to as the degree of the numerator and the degree of the denominator, the don and the dod. The degree of the numerator, our leading term is this x, and it has a leading coefficient of 1 and an exponent of 1. I care about the exponent, about being a 1, and so that's why my degree of the numerator is 1. My degree of the denominator is 2. Look at the leading term. Its degree is 2. I don't care about this coefficient right now. I just care about the degree being 2. And this is what we refer to as bottom heavy, which I'll come back to in a minute when I get to the next page. All right, so just review. So we know that there is a domain restriction of f of x whenever I see a variable in the denominator. This denominator, or really whenever I see a fraction, but this denominator cannot equal 0. So take the denominator, set it to be not equal to 0, and then solve for x. And when I do, I get that x is not allowed to equal 2 or negative 2. If I plug a 2 into here, I would end up with 2 squared minus 4, which is 0, and I would get something over 0, which is a no-no, that is undefined. So this is, so 2 or negative 2 does not work. They are not in my domain. So whatever that means, when I'm going from negative infinity, trucking along, coming to the right, the moment I get to negative 2, there's something happening at negative 2. It might just be a hole, it might be an asymptote, but there's something happening that the function is going to just hop over negative 2 in one way or the other, have something from negative 2 to 0, and then hop over 2 and going on to infinity. So there's something that's either a hole or an asymptote. So let's talk about how we can maybe tell which is which. Well, the way that we can tell is by factoring. So we need to factor the top and the bottom and see if anything reduces. So here I can reduce, after I factor the denominator into x plus 2, x minus 2, I can reduce this x plus 2 on the top with the x plus 2 on the bottom. They reduce to 1, and I'm left with 1 over x minus 2. Now from graphing transformations, you should know what this function looks like. It's our function 1 over x that's just been shifted to the right 2 units. So you should have a pretty good idea about what that looks like in your brain. But what is this thing? What happens to this? Well, since this is a part of my function, notice we knew that there was a vertical asymptote just from this graph at positive 2, because we've gone to the right 2. But I said just a second ago that x also couldn't equal negative 2. Well, that also has to be true about the entire function f of x. When f of x equals negative 2, even when I technically put it into this form, it still is not allowed to work. So let's take a look at our graph. So I know from graphing just 1 over x minus 2 that I can go to the right 2, and then I can graph my function. I go over a half up 2, over 1 up 1, over 2 up a half, and then the same dots on the other side. Negative half, negative 2, negative 1, negative 1, negative 2, negative half. And I can get these dots. We get these dots just from our knowledge of transformation and parent functions. So that means that I know then that I have a horizontal asymptote at at y equals 0, and a vertical asymptote at x equals 2. Which I actually just realized I don't have my HA labeled. Bad me. So I need to label my horizontal asymptote is y equals 0. There we go. All right, so let's put out a list of things that we know from this function. I know I haven't talked about the whole yet. I'll get there in just one sec. So my domain, if I read it in set notation, it's a set of x's, just not when it's positive or negative 2. Or we can say from negative infinity to negative 2, union negative 2 to 2, union 2 to infinity, with parentheses on all of these because we're not touching the 2 and negative 2. I have a vertical asymptote, that's this vertical line here, at x equals 2. Way that you can keep track of whether it should be y or x equals, think about the axis that you're crossing. So this vertical line is crossing the x-axis at 2. Basically imagine my tick mark at 2 is just stretching to be really, really tall. So it's at this x equals 2. I have a horizontal asymptote at y equals 0, this line right here. Again, I'm crossing the tick mark here this way, this line, this horizontal. I'm crossing the y-axis. I am on the x-axis, but I'm crossing the y-axis, and so that's y equals 0. This particular function, if I were to graph it, is not going to touch the x-axis because of the asymptote and our knowledge of this function. And then our y-intercept we see here is at 0, -half. So all this is stuff that we should be able to figure out previously. The only thing that's really new is this business about, real fast. We also knew about our y-intercept because I could just plug in f of 0. So if I plug in f of 0, you can plug it into the reduced function or the original one, and we end up with a -half. So that's also how I knew that it was there. All right, so now let's talk about this thing called a hole. I'm going to actually jump over to Desmos again. And I'm going to type in this function. So I'm going to have I'm going to have x minus 2, it's plus 2, I think, plus 2 over, I'm going to do parentheses, x plus 2, x minus 2. All right, so here is our function. I'm going to point something out. So we have, this is what we were sort of kind of sketching earlier. The rational function just shifted to the right 2. But here, notice what happens when I swoop over to -2. The moment I get to -2, it's -2 comma undefined because we have a hole. And you see how there's an open circle at -2 because, like I said, there's a hole. Now I want to point something out. If I change the x plus 2 in the denominator to be, let's say, x plus 3, we go from having a hole to now having 2 vertical asymptotes. We have a vertical asymptote at 2 and a vertical asymptote at -3, at x equals 2 and x equals -3. And the function at x equals 2, well, that's fine. That's just when we have an x-intercept. So what's happening here is that x plus 2 and the x plus 3, they don't reduce. So because it doesn't reduce, it doesn't get eliminated from the function. So that means we don't have a hole. We would actually have 2 vertical asymptotes. All right, so how do I know that there should be a hole? I know that there's a hole at -2, but how do I know that there's a hole at -2, comma -4? Well, what we do is we evaluate the function, the reduced function, where our hole is. So now if I plug in -2 into this original function, I'm going to get undefined. But once you reduce it, I'm not going to get undefined when I put it in here. So I can see where the hole, where the function approaches. Remember our approaches notation? How when our function approaches from the left versus from the right, how it's approaching -1/4. I'm not going to equal -1/4. I'm just approaching -1/4. So if I plug in a -2 here, we end up with a -1/4. So we have a hole, air quote hole, at -2, comma -1/4. All right, it's enough of a sort of a setup. You see what's going on. Let's write some notes down so we can have some definitive stuff that's happening. All right, so how to find our vertical asymptotes, holes, and our horizontal asymptotes. All right, so vertical asymptotes, we're going to abbreviate to be something called VA. I just abbreviate to be VA because I'm lazy. And then holes, the full name of holes is a removable point of discontinuity. Now, it's a point because, as we see, it's literally a point, a graphical point. It's discontinuity. It has discontinuity there. It's not continuous. The function, if I was to be graphing, I have to pick up my pencil and hop over the hole. It is discontinuous at the location. The reason why we call it removable point of discontinuity is because, well, literally, it's gotten removed from the function. Do you see right here? I removed it from the function. I don't see its effect in the reduced function. Now, it is in the original full full function, it is there, but we call it a removable point of discontinuity. Okay, 3 steps to finding your vertical asymptotes and holes. So first, here we have this fact. The vertical asymptotes and our holes are located at our domain restrictions. So step 1 is to find our domain restrictions, like we did many lectures ago. So find your domain restrictions by setting the denominator to be not equal to 0, and then solve. Remember our acronym. If I have some number over 0, that is a no-no, and that's undefined. So step 1, find your DRs, find your domain restrictions. Then, basically, we're now sorting every factor, every individual factor can either be a hole or a vertical asymptote. It can't be both. Now, I might have 2 factors that are on the same spot, kind of like a double root, and one be a hole and one be an asymptote. Then in that case, like the asymptote wins. But each specific factor gets sorted into either being a hole or being a vertical asymptote. So if I sort them into a hole, then I know it's not a vertical asymptote and vice versa. So let's find the holes first. So to find holes, we need to factor both the numerator and the denominator. If any factor is reduced, then there's a hole at the x value, which makes that factor be 0. We should be getting pretty used to, here's this factor, set the factor equal to 0 to see the x value, basically solve for x. So it's that same idea. So whatever our factors are, set them equal to 0, and at that x location, there's a hole. All right, which basically is that corresponding domain restriction. And then evaluate the reduced function at the x value to find the hole's y value. So that is this right here. We knew that we knew that with the factor x plus 2 that there was a hole. So we take x plus 2, set it equal to 0, and we knew that there was a hole when x equals a negative 2, all right, which was one of our 2 domain restrictions. So then the second part is then we take this negative 2 and we plug it into the reduced function. So I plug in negative 2 into this reduced function and simplify, and we ended up with the y value of the hole being a negative 1/4. So that's this part right here. Evaluate the reduced function at the x value of the hole to find the hole's y value. Then any factors that remain, any factors that you have not reduced in the denominator, big point, in the denominator, correspond with vertical asymptotes. So what I mean by correspond, meaning the x values which make those zeros. They are the domain restrictions, or set them equal to 0 and solve. So make sure they're clear that it's in the denominator. I'll talk about what happens if it's in the numerator in a second. All right, so that's vertical asymptotes and holes. Factor to determine set the denominator equal to 0, which might require you to factor it. Solve for x's. Those are your domain restrictions. Sort them into either being a hole or being a vertical asymptote. If it reduces, it's a hole. If it doesn't reduce, it corresponds to a vertical asymptote. All right, next, the horizontal asymptote. So this is where us knowing the don and the don come into play. The degree of the numerator, degree of the denominator. So the degree of the numerator could be bigger than the degree of the denominator. We affectionately refer to that as top-heavy. The degree of the denominator and numerator could be equal to each other. We call that equal powers. Or the degree of the denominator could be smaller than the degree of the degree of the numerator could be smaller. We call that bottom-heavy, or the bottom could be bigger. If it's equal powers, meaning the degree of the numerator and the denominator are the same, then every time, all that you got to do is you want to look at the digits, look at the leading coefficient, and it's just a over b. Do not give me n over m, it is a over b. All right, lastly, the one that we nicknamed bottom heavy, this one, the dod is bigger than the don. They are easy, it's automatically y equals 0. All right, so that's how we determine our horizontal asymptote. If it's top heavy, it's going to be potentially a slant asymptote, and we have to do some division. If they're equal powers, then you look at the leading coefficients. And if it's bottom heavies are easy, nice big old bottom. We end up with just y equals 0. All right. Lastly, let's talk about finding our x and y intercepts. So for finding our x-intercepts, we set the reduced numerator to be equal to 0 and solve. Why reduced? Well, because it doesn't matter whether it's reduced or not, and if it's reduced, then it's just easier math. And also because if it's reduced, I know that that value that's a whole is going to go away, so just make it go away. So set the reduced numerator to be equal to 0 and solve. Remember, if I have 0 over something, that's okay. That's just equals 0. So that's the gist about around here. Here's a little bit of a proof for it. But if I have a function, it's p of x over q of x, and I know that this equals 0, well then I could multiply both sides by q of x, and q of x times 0 is 0, so it does not matter what this denominator is. This denominator is affecting quite a lot of things, but it is not affecting the x-intercepts. It has 0 input in the x-intercepts, just like the numerator has 0 input in the holes and vertical asymptote because of the domain issue. All right, so don't let that bother you. So it's so what drives the x-intercepts is all about the numerator. So set the numerator equal to 0, solve, there are your x-intercepts. And then how do you find the y-intercept? Just like we've been finding y-intercepts all year long. Plug in 0 into the function. So make x be 0 and solve. And you can put this in, simplify. You may plug this into the original or into the reduced. In my opinion, it'd be easier to put into the reduced, most likely. All right. So we have a few examples that we're going to walk through.